as people are grabbing food in the back, we can go ahead and start at least some of our thought process, discussions. And actually before that, I think we need a question asked by Mr. Hicks. So we've done some extra help sessions, or I should say they have. I didn't have anything to do with it. Akia Joyner, where's Akia? Is she here somewhere? Oh, there she is, hiding in the back corner. And Evan Hicks and Sarah Kaufman have been doing some study sessions. There was no one that came to the ones last week, so we didn't want to run them again if no one is planning on coming. So what we're going to do, what do you want to talk about? You're going to ask what are the times on Friday?
Friday, 2:30 to 4:30 and 6 to 8.
2:30 to 4:30. 6 to 8. And then is Akia, did you email me say you're out of town for one of these two, or? So is this still happening? Is this only you? And then Saturday, are we doing the one?
Well, I feel a lot of fun, but I had a lot of shit on it. I would have done well. I didn't know anything. Like, I still haven't so much of it. But I didn't think it was that hard.
Okay, so I'd like to see a raise of hands to make sure if we put an effort to, John Paul, if we put an effort to have these sessions, we want to make sure that someone's planning on showing up, because if we're just sitting around, it's kind of a waste of our time. So the top session, raise your hand if you plan on going to this, 2:30 to 4:30. It's a study session with Evan. Okay, so we have 2, 3 people. Okay, so it sounds like that is worth, Evan, is that worth time? Okay, and so anyone else is welcome to drop in. We will do that session. Evan's second session is Saturday 12 to 2. Raise your hand if that's a time where you might be on campus and want to go to a study session. We have 2 in the back, 3, 4. Okay. So remember, next week is an exam on Wednesday, so that's why it might be more popular to go this week. So basically the setup is that they're there to help you. If you want to bring in stuff from your workshop before lab that you weren't able to get through, or class material, parts of the worksheets we didn't get through, or homework questions, or other conceptual questions, they're a great time to go ask. Evan has a really good handle on stuff. The other one is office hours on Friday. Does anyone plan on going to that 1 to 2:30? It's kind of an exam review session if we want it.
Are you having anything next week?
I will have...
Like on the day of the test?
The day of the test I will. That's kind of too late to do a lot of the big concept stuff. But it's the time to brush up. Yes, so next Wednesday we'll have it from 3:30 to 5. So as far as this one on Friday, who's planning on going? Monica, Mike, okay, so that's this one out here. So it looks like
Saturday.
All right, would anyone be, I heard Thursday morning discussion about Thursday morning being better?
Like tomorrow morning?
Yes, tomorrow morning.
I'm going to be at all of them.
Let's do, how about tomorrow at 10 to noon? Raise your hand if that would work for my office hours instead. 10 to noon tomorrow. John Paul, does that work for you? Okay, so let's do this instead. The one with me is going to be Thursday instead this week, 10 to noon, and ETAS 125. I'll send that out in an announcement as well, but it's good to get some feedback from you all. Okay. The other thing, logistics-wise, John Paul, you all right? It's okay. The other logistics I wanted to talk about was that there was just a Friends of Medicine, Science and Medicine seminar series. That's where the food came from. We had about 30 people show up, which is a decent attendance. There is Olive Garden food that we provided this time. I'm not sure what we're going to do next time, but something along the same lines. And next time it's an anesthesiologist who is working with opioid epidemic, and then the guy who runs the North Little Rock Innovation Hub. So that's November 20th, Wednesday, November 20th. Put that on your calendar. It's before this class, the last one before Thanksgiving, I believe. So there is an RSVP. I'll send out an email again with a website to go to. It's the same website. There'll just be a different link to click.
Will it be the same time?
Same time.
I don't know anything about
4:30 to before this class. All right. So today's class, we're going to spend the first quarter of class talking about some of the concepts of limiting reagents and balancing equations and percent yield. Then we're going to shift and we're going to kind of backtrack as far as where you were in the semester and do the stuff that you worked on for your pre-class primer, which is precipitation, net ionic equations, and some of those things. So that's what we're working on today in class.
That pre-class primer we had when we were doing ionic, what was it called, equations and net ionic equations, is that going to be on our test?
Yes. Everything up through Monday's class is on the test. Unfortunately, in this class, we don't have time to stop and do a whole review day because we have 3 exams during the semester. It's like 3 out of our 20 classes are already taken out from exams, and so we kind of need to keep forward momentum. So that's what we're going to be doing in class today and Monday.
So wait, this third exam is our last exam?
Third exam is the last during the semester exam. The fourth exam is a cumulative exam, and that's during finals week. All 4 are equally weighted, unless you do better on the final than one of the others. And the final score counts in place of your lowest exam score.
So the final's going to have
Everything.
Cumulative plus extra information you're going to give us after this exam?
Extra concepts we will be working on between the third exam and the final, yes. But we have 2 hours to take that exam, so it's much more relaxed. And you can show me what you're capable of. It's great. No, it's longer because you have 2 hours and you have to show the entire semester as well as the last 3.
Just as stressed, but it's longer.
No, you were relaxed because you got to show me how much you know. So, with that said, I want you to start out with question number 1. How do you correct the sentence there? Go ahead and write it down on your own. Look at the statement. If you don't have a worksheet, does everyone have a worksheet? Okay. We have some lots of people here. It's a new one. Nope. I want you to write down on your piece of paper how you would correct that statement. Once you've written down your response, then you can check with the person next to you. All right, who wants to write on the tablet to correct this statement?
Oh, I don't want to correct it. I just wanted to write it.
Who would like to correct the statement on the tablet? You good?
I don't want to break it.
All right. What do y'all think? So Tay crossed out grams and put moles. Can you explain why, Tay?
The ratio is moles to moles, not grams to grams.
Good statement. So whenever we see these balanced chemical equations, the reason I keep bringing this up over and over again is because it's one of the most common places that people will make a mistake. They'll say, well, if I start with 2 grams, I can make 8 grams of carbon dioxide. And we need to think about that as how many of them, not how heavy they are. So we're going to go ahead and work on a problem in a second that has us applying this and working through it. So my objectives for you today are, with the given amount of reactants, to be able to predict the theoretical yield from a reaction. We can also do it the other way around. If we know how much product we want to make, we have to say how much reactant do we need in order to make that. Interesting. This, if you notice, that sentence had "at most" you can make, because that's 100% theoretical yield is what you can make. So we're going to talk about what happens when you don't make 100% theoretical yield. And this idea of the most you can possibly make is your maximum, and what happens if we make less than that, can we calculate theoretical yield. The last part is going to be based on the pre-class primer, talking about net ionic equations and how to look at solubility reactions, precipitation reactions, which we've looked at before. But let's go ahead and work on a little bit of a challenging question. I believe this is question number 2. Take a minute and think through the process first, and then start to work on it.
Okay, and so since you got O2 is 15.99 times 2, and you're going to take out the amount of okay, so it'd be that's the whole amount.
It would be like 1 mole of oxygen is like a fraction of a mole of oxygen. The octane is like so it'd be like a fraction of octane. So I think the octane
I mean, yeah. Because you use the whole. Well, it could be wrong, but I didn't. So for every 2 moles of octane, you need I think I can figure it out. So you're gonna run outside. Shut up, Martin. Also, are you not confident about the video?
So you divide the 30, so it's like
I'm worried about it. How are you sitting? Outside of credit. Okay, good.
Yeah, I didn't use the product. I did it with oxygen. I did it with oxygen just to see which one would be hurt.
So let's take some time to unpack this question. This question relates very much to the s'mores question that we did in class on Monday. If we have 30 grams of each of these, if I answer C, what would you tell me?
They don't each weigh the same.
We have the same mass of both. So they technically, the piles weigh the same, or the amount of starting materials weigh the same. Can you be more specific? What misconception might I have if I said answer C? That the limiting reagent is based off of the mass. And in this case, that's not true. And it actually comes down to what Tay said, that maybe I'll enhance her statement, that if they had the same molar mass and we had the same weight, we would have the same number of moles of both, so that would be something to consider. But if we have the same number of moles of these two reactants, does that mean that neither one is limiting still? Because we need 25 oxygen molecules for every 2 octanes. So we need to have a lot more of the oxygens than we do the octanes. So how do we actually calculate this? How do we figure out which one of these runs out first? Because it's much more complicated than just saying how much do they weigh. So can someone talk me through what they might do in order to answer this question? Big picture, process-wise if we can. Not the exact numbers you calculated. Kind of like a solution map. Even more high level than the solution map. What do we need to calculate to convince ourselves that one of them will run out first and be called the limiting reagent? Is that what the question is? Which one would be the limiting? Yeah. I saw a number of people do this in different ways that were useful. We need the molar masses, but what do we do? What are we trying to calculate?
So, like, would it be like you need to find the molar mass of 2 moles of octane and the molar mass of 25 moles of oxygen gas, and then compare the two?
So there's something I'm going to tweak a little bit what you said, but we'll come back to that in a little bit. So what are we trying to do? If we knew the molar masses, we know the molar ratio, what are we trying to find? What allows us to answer this question?
Which one we need more of?
I'm going to tweak that a little bit. Donald?
How much CO2 would weight 15 grams of the CO2 tank?
So that last statement, the very first statement on there, at most we can make, right? I want you thinking in that mindset. So the mindset is, if we use up all 30 grams of octane, what would be the most CO2 we could possibly make? That's half of the answer. What's the second part of it?
Which one runs out first? Which reagent runs out?
So in the end, yes. So what I want to know is, if I use up all 30 grams of octane, what's the most CO2 I can make? If I use up all the 30 grams of oxygen molecules, what's the most CO2 I can make? Once we do that, we say, well, we're only going to be able to make as much as the limiting reagent can make. Right? If we run out of graham crackers and we can only make 5 s'mores, we're not going to be able to make 6 s'mores because we ran out of graham crackers before we made the 6th one. So the calculations we need to do is, how much can we make from this? How much can we make from this? And then which one runs out first? So do you want a minute to write out what that would look like, or should we work through it together?
Work through it together.
Okay, we'll work through it together. So would someone like to talk me through it? Olivia, would you like to talk me through it since you were talking about the technical details there?
I don't know if it's correct though, but we'll give it a go. Okay, I started with what was given, which was 30 grams of octane. And to get rid of grams, I figured the molar mass of octane, which I came up with 114.23. So that goes on the bottom, I cancel it out. Over 1 mole of octane. And then to get my answer in mole.
So pause 2 little things real quick.
Okay.
The 2 things are, 1, in class, if you are now comfortable finding the molar mass, Google it. Don't waste time calculating the molar mass. It takes a long time. I want you to show me once on the exam you can do that, but every other time I'll either give you the molar mass once or twice. So as long as you're comfortable finding it, just Google it. Save us time in class. The second one is terminology-wise. We're going to say that we're not canceling out grams. Mathematically it's true. But we're converting from grams, the weight, to moles, which is how many?
Right.
Great.
So, at first I stopped there, but I started thinking about it. I want to use my molar ratio. So I used, for every 2 moles of octane, I had 25 moles of oxygen. And then I
For every 2 moles of...
octane, I had 25 moles of oxygen.
Okay.
And then I came up with the number 3.28 moles of oxygen. And I did the same for, wait, oh, you kept going. Okay, never mind.
Okay, so what's really cool is that Olivia just showed something we didn't even talk about. She showed us something another way to solve this problem. There's one more step I would add, and that's that 1 mole of O2 weighs 32.00 grams. What did I just calculate if I finish this series of calculations? Can someone put in a sentence? We're going to have the units is grams of O2. Do we have a number for that? Can anyone calculate that? Can you take the number you had for the moles and multiply it by 32.00?
104.16. Oh, that's how we do that first.
Okay, so what did we just calculate?
Grams of oxygen.
It is the unit of grams of oxygen, but in what context? Shelby? Can you say it one more time nice and loud? I couldn't hear you completely.
And grams of oxygen is needed for it to react with 30 grams of oxygen.
Did everyone hear that?
No.
I'll say it one more time just to repeat the amazing statement that Shelby had. This statement right here says, if we're going to use up all 30 grams of octane, how much oxygen do we need? That is absolutely a legit way to answer this question. So it says if we use up all the octane, we need 104.96 grams of O2. Do we have that? We have 104 grams of O2? We have 30 grams. So what does that mean? What does that mean?
You're just running right out of oxygen first.
That doesn't mean you ran out.
It means that we have nowhere near enough oxygen to use up all of this. But that means that we only have 30 grams, and that means that we're going to run out of oxygen first. Okay, so what's the other approach that a lot of people did? Similar approach. Say what this calculation? So this calculation says if we're going to use up all 30 grams of octane, we need this many grams of O2. Because of the molar ratio, we can find how many octanes we have, and then what the molar ratio tells us is how many moles of O2 we're going to need, and then how heavy they are. So this is how much we need to use up all that. Since we don't have that, we know we run out of oxygen first. So totally legit approach. And I'm going to maybe show the other approach that I think a number of people in this room did.
But can't you look at the equation and
Can we look at the equation and get what?
you should know, I guess not. Never mind. Abort.
Okay, so let's answer the other question. So the other question is, if I use up 30.0 grams of octane, I need to know how many of them I have, right? 1 mole of octane weighs 114.23 grams. And then I can say, well, how much CO2 can I possibly make? What's the most I can make? So what do I put next? What would I need to have next to answer that question of how much CO2 can I make? Over? For every 2 moles of octane we use, we will produce at most 16 moles of CO2. And then I want to know, well, how heavy is that CO2 that I make? So I could say then every 1 mole of CO2 weighs, 44.0, can't remember the number, 0.01 grams of CO2. Did anyone calculate that? I think I saw a lot of people calculate that.
It's 92.63.
Okay, what is that value? What is the sentence I use for this line that I just calculated out?
Octane can make up to 92.63 grams of CO2.
Great. So what Donald just said is that for every 30 grams of octane, we can make at most 92.6 grams of CO2. Let's do one more calculation like that, but let's say we start with the 30 grams of O2 molecules. That was the other starting reactant. We want to ask the same question. How much, if we use up all of the oxygen, how much CO2 can we make at most if we use up all of that? So what's my first conversion factor I use here?
So 1 mole of O2 over
32.00 grams per mole. And then what do I do next?
The ratio,
So what goes on top?
25.
16 moles of CO2.
For every 25 moles of O2 I use, I will need 16 moles of CO2. So if I stopped right now, I'd know how many moles of CO2 I could make. If I want to know how heavy it is, what do I have to do last?
Convert it back to grams.
Divided by what?
I said convert it back to grams.
Convert it back to grams.
Why do we have to know the grams?
I'll get to that in 1 second. Okay, so what numeric value do we find here? Who calculated this? I know some people did.
26.4, did I get the right thing?
Grams of CO2. So if we use up all of the octane, we can produce at most 96.6 grams of CO2. If we use up all the oxygen that we started with, we can make at most 26.4 grams of CO2. What can we conclude from that? Talk to your neighbor for a second. I hear a lot of silence. What can we conclude from these two lines here with the mass of CO2 that we can make? Follow? Okay, good. Coming back to your question.
We got a ratio right here. We know we need 2 and 2. We know we need 2 and 2. And they calculate the way with 2 and 2 from if you're looking at
Legit. But that involves that you really understand how mass plays into number, and so that's a different approach. That might be way easier for you.
okay, so I'm not going to count on
If you can clearly show what you're doing now. All right. Can I have a concluding statement based on these two lines? These. It'd be great to hear from some new voices. Take a stab at it. We can always modify our statements. Kai, would you like to share what your group talked about? How those two lines fit together?
Okay, so, looking at the amounts that we got from both the bottom two, we could say that, oxygen is a limiting reactant
Why?
because it will run out first compared to the other.
Great. So you can say that the oxygen runs out as soon as we produce 26.4 grams of CO2. We're never going to get to this amount because we ran out of the other one first. Is there another way that your group put the sentence together? There's lots of different ways to say this. Are we happy with that? Do we have questions about that?
Could you say the sentence one more time, how you would write it down if you asked us? How would you verbalize this sentence in a complete sentence?
So I can add an additional way in saying that if we use up each of our reactants, we see that we can make less with one, so it runs out before we're able to get anywhere close to the second one. So the one that runs out first is our limiting reagent. The top line, which is maybe what Olivia was doing, maybe I hijacked it for something else, is another way of saying it. It's saying, in order to use up one of the reactants, how much of the other one would I need? If I don't have that, that means that that's a limiting reactant. If I have that, it means this is a limiting reactant. So Lena asked me, she said, why do we need to calculate the mass at the end? Well, there's a few things that she asked me. But one of the questions that I got from a couple students is, do I really need this last step? What do you think?
Yes.
To answer question number 3, the answer is yes. But to answer question number 2, the answer is no. If all you're trying to say is, how much can I produce with this? How much can I produce with this one? Moles will tell you which one you can produce less of, so that's fine. You can then say, well, how much do they weigh? And that's going to be proportional. So this is going to be about 4 times as much as this one in moles or in grams, because the molar mass is the same of both. So we could have done this, and we could have, instead of calculating how many grams of CO2 can you produce, we could have said how many moles of CO2 can you produce, or how many grams of H2O can you produce, or how many grams of H2O can you produce. Any of those will allow you to answer which is the limiting reactant, which one runs out first. Any questions? Can you do this? That was a nice strong yes. Okay. So let's, instead of asking this question, let me see what my next question. So my question now is, well, in this reaction, we actually only made 1.49 grams of carbon dioxide. What is my percent yield for this reaction? So this is question 4. The fill in the blank is 1.49.
Like, if you run out of 26. So you can't make more because you are running out of power.
All right, we have 5 responses. Please click in your response if you calculated this. All right, we're taking a long time to answer a question that should be about 20 seconds. So what's going on? Where are we getting stuck?
Which ones are theoretical?
Shelby, is that what you're going to say? Or? Absolutely. So this is based off of the answer to number 3. That's our theoretical yield. So what is our theoretical yield? Is our theoretical yield 92.6 grams?
I thought it was 26.
We couldn't make that much, right? We ran out of O2 way before that. So what's the most we could possibly have made?
26.4.
26.4 grams of CO2. That's the most we could ever possibly make. That's if we had a perfect reaction and every single O2 got used up. But that is not how life works. There are reactions where you get most everything gets converted, but a lot of times it doesn't happen. So in this case, we got 1.49 grams. And we could have gotten up to 26.4. Is that a good reaction? It's pretty crappy. So do we have 100% yield? Nope. So how do we calculate it? Or you could just say we divide that by how much we thought we might be able to make. And then that's a percentage, so we can multiply it by 100 to get the actual percentage value. So what does that end up being? 5? 5.64%. Okay, so maybe the confusion was you weren't sure which yield we were going off of. What is the theoretical yield? So hopefully this part we've gotten the hang of. Okay? Great. Sometimes I don't ask the clearest questions, and then you should weigh me down and say, hey, clarify something. All right, so now we're going to switch gears a bit, and we're going to go... at the end of this slideshow, by the way, I have some practice questions for what we just did. Also on last class's worksheet, there's a number more questions about calculating the limiting reagent, or calculating from how much reactant to how much product to how much reactant. So those are all really good study tools to bring to these study sessions, work with your peers on. And if you are working on one and you don't have a chance to meet with someone else, post a Blackboard discussion, a picture of your work, and say, I got stuck. What am I doing wrong? Or is this answer appropriate? Is the process appropriate? And I can answer there. So now we're going to switch gears, and we're going to start going back to the lab that you did. You remember this lab where you combined 2 different liquids together, and then you either got it being cloudy or you got it being clear? So that process was called precipitation. And we're going to talk a bit about that, and we're going to do some things related to writing out a chemical equation around that. But to start with, I want to think about the theory of why certain things precipitate and why others don't. So if we have a salt in solution, what charge is a cation? Cation has, or a salt has a positive component and a negative component, right? So I'm asking the question, it dissolves in water because it's attracted to water. What part of water is the positive cation attracted to? Go ahead and click in your response and then check with your neighbor.
Like, are you asking which one would you say is the cation whenever water splits?
It's not an ion. Nope.
Repeat how you just said that. Repeat the question how you just said it. You just say it the same way as me.
So the question is, if you have a salt, the most basic form is a plus and a minus that make an ionic bond. If you put that in water, water separates them. What part of the water molecule, is it the hydrogen, or is it the oxygen, or is it random, is going to be attracted to the cation?
Okay.
We have 45 responses. Do we need another few seconds? Feel all right? 46? All right. We have a majority answer in the class. Would anyone like to explain what you answered and why? No?
I'm almost done chewing. The hydrogen atom, the oxygen atom would be attracted to the cation in the solution because it's got a negative charge.
Because it what?
It has a negative charge.
Okay, so we have this idea that opposites attract when we're talking about charges. So, how do we feel about this exact statement? You like how fast I can transcribe your speech?
I know. I can't trust questions. We've been scarred. We have PTSD.
Okay, closing out.
Because nursing is like frat our brains, we want to make everything a lot more complicated than it needs to be.
We had a big tank today. What? That defies.
Why? Why is this statement false?
It's not the only reason.
What is the false part of this statement? Talk to your neighbor. I'm going to give you about 30 seconds. Try to figure out what is false about this statement.
Wait. For the exact same reason.
What's that?
I would take negative charge.
So what's wrong about that? That's an incorrect statement. What's wrong with that?
Water is going to dissolve.
We're not supposed to do it until it's we're supposed to do
Is anyone burning to share their realization?
I didn't realize. I didn't catch it.
Okay, so I think it is it's because there are like times that you would drop something in the water and it wouldn't be soluble. So those, the opposite charges wouldn't attract.
Okay, so your statement is true that there are certain ions that do not separate because water is not attracted to them. That's not what we're getting at with this question.
But that supports why it was false.
So if something does dissolve, question is what part of this is true. Ankar, can you share what you guys discussed?
It's a partial negative. Don't ask me to elaborate.
So this statement says that water has a negative charge. What has to be true for something to have a negative charge?
More electrons.
Has to have more electrons than protons, which means it has to be in a bond where it stole an electron away from something else. Do we have any ionic bonds in that molecule?
Yeah. Wait.
No.
Crap, sorry. That's what I meant.
These bonds are not ionic.
That's right, they're not.
They are polar. And polar bonds give a little bit of a negative charge to oxygen and a little bit to hydrogen. And that's true for each of those two bonds. That's what makes water one of the most amazing solvents around, is that it is very polar, meaning it has a significant partial negative charge and a partial positive charge distributed throughout the molecule. But if you take that into account and you say, oh, you have an ion with a positive, a full positive, if water was charged as well, we would have a 1-to-1 ratio and they'd be able to be attracted. It'd be an ionic bond between water and salt. That's not the case at all. So this overall dipole of water molecules is what allows them to interact with other molecules that have partial positives and partial negatives, aka other polar molecules, and be attracted to them. It allows tons of things to dissolve. Some of those molecules have full positives and full negatives. And if that's the case, one sodium chloride would look something like this. we would have tons of partially negatively charged oxygens pointed towards the cation. And then the anion would have tons of the partially positively charged hydrogens pointed towards it. But these do not form ionic bonds, they form electrostatic interactions. Like a balloon, when you rub it on your head and you put it on the ceiling, it sticks, but it's not forming a completely new substance that's bonded together. Question, Tay?
So the first question on the last page was the answer C, that there wasn't.
First part was, it is the oxygen in a water molecule that points towards a cation. That's what's most attracted. But it's not attracted because it's a full negative. It's because there's a partial negative. So it turns out that in order for a cation and an anion to be pulled apart, they're really attracted to each other, right? A plus and a minus. There's reasons for those to stay together. So there have to be a lot of water molecules that come and surround each cation and each anion in order to hydrate them. Solvate is another word we use. Hydrate kind of makes sense, like you drink a lot of water to hydrate, right? Ions hydrate by surrounding themselves in water. And that basically shields this positive from this negative and pulls them apart. But then Olivia had a strong point. She said sometimes that doesn't happen, right? When you combine two different solutions, sometimes you saw those ions would slap together from different compounds and they would fall out of solution. They would say, screw you, water. I would much rather be together with that ion, and I'm going to come and I'm going to push through all of these, and we're going to be attracted and we're going to fall out. That's what precipitation is when those ions have a stronger attraction for each other than they do to the water around them. So when you look at that solubility table, do you all still have that solubility table? If you look at that solubility table, that summarizes what we find in nature. When you have certain ions, if you have a sodium ion with a chloride ion, water is going to be able to go and separate those because of the partial charges on water. But if you have sulfate and calcium, let's say, we put those together, water can't push those apart. And so those will stay together and those will precipitate. Do you have something you wanted to add?
I agree.
So if we did a little animation, if this is sodium chloride, then every single water molecule that's moving around would have some attraction to a different side of the water molecule, to a cation or anion. So what is that larger of the spheres? Is that a positive charge? Is this thing in the middle here positively charged? Or is it negatively charged? How do we know that? Because all the positive parts of hydrogen or water are connected to it? Is that a good statement? Because all the partially positive parts of water are attracted to it.
Partially positive water.
So this is a negative anion. We know that because water's partially positive hydrogens point towards it. And we can see that the opposite ion has the other side of water coming and being attached to it. So there is a homework problem that you have this weekend in your homework that has, or hopefully not this weekend, this week, right? We're starting on that tonight or tomorrow?
Yeah.
That actually has you download a Java animation that shows pouring salt into water, changing the solubility of the salt, the attractive forces between them. So hopefully you can download that. You might need to change the security settings because Java is kind of outdated. But I advise that you check that out, and it helps you visualize how those salts going into water. Some parts separate, some parts don't. So what about the molecular compounds? So let me do, if we have glucose, can't remember exactly where all these go, but something like this. That's about what glucose looks like. What is glucose? Sugar, right? So this is, glucose would be table sugar. That's what that molecule looks like. If that last image had been glucose, would the exact same thing have happened? Would water have come in and pulled apart atom by atom until it's all dissolved? It absolutely dissolves. Kool-Aid is the best example. Oh, yeah. So why is that wrong? Why does this molecule not get pulled apart atom by atom? It is soluble. There's two types of soluble. One is if it's ionic, the ions separate from each other. And remember now, an ion can be carbonate. That's sodium carbonate. When this dissolves, that ion stays together in the middle. And the two sodiums separate. So that splits into three components. So what happens to glucose when it dissolves? It stays the same. It dissolves because you can boil off the water afterwards and you still have sugar, right? Or you can put it out in the sun, you spill it on the table, and it's still sugar afterwards. It's either sticky or it's crystalline. So what happens is that you have multiple, I don't know how to draw another one quickly, but let's draw another ring, right? So if you have sugar, you have multiple glucoses stacked on top of each other that are attracted to each other, and they form a crystal. Water can go between those and pull apart the molecules, not the atoms within the molecule. So there's a big difference between how molecules dissolve and how ions or salts dissolve. What's the biggest difference you can see? If I gave you a formula, how could you tell which one of these two processes would happen? Whether it's pulled apart into many different pieces or whether it just separates the components from each other? Relates back to net dipole. So if I give you a compound like this, and I say, is that going to separate into individual elements or ions, or is it going to stay together when it dissolves? How would you answer that question? How would we know? Courtney? So we look for ionic bonding. And if the answer is no, like in this case, then they stay together. Here we have a metal with a polyatomic ion. Or we can have a metal, NaCl, right? A metal with a nonmetal forms an ionic bond. A metal with a polyatomic ion forms an ionic bond. When those go into water, those ionic bonds themselves will separate. But if you have a molecule, it dissolves, gets surrounded by water, separates from the others of itself, but if you boil off the water, it'll come back together. Another good example, I'm sure no one here enjoys, is ethanol.
Is what?
So ethanol can dissolve in water, but it stays the same. It doesn't separate. We don't have the O and the H separating. We have the whole molecule staying together. Ethanol is drinking alcohol, for those who don't know. Okay. So let's think about what that looks like. So we have, if you flip over the back side of your page, we have a strong electrolyte, potassium sulfate. Which of these beakers represents what would happen when potassium sulfate is dissolved in water? And you'll notice we're not showing the water molecules here because it gets really busy when you show all the water molecules. So you see the little letters in the bottom to decide which one?
What does it mean? I was talking about an ion or a molecule.
This one's completely broken down. Yeah, I feel you.
Yeah, they are all supplied, but like, the charm, sulfate is negative too. So that's only a 1. Oh, wait, but it will be, is it? For sulfur and so it is actually
Let's do another 15 seconds. Is all the food eaten? Peter? Is all the food eaten or? It looks like you used it. Molecule is O2. Okay, so step 1 is
Determine if it's ionic.
even before we determine if it's ionic. All right, we need to know what the formula is. So remember all that stuff I told you before about you're going to need to use this over and over and over again. That's why I test you on it. It's because it's going to come back to haunt you. So K2SO4. Are there any ionic bonds? That's the next question. Yes? No? We have a metal, potassium, the non-metal, polyatomic ion, sulfate. So what happens when that dissolves? What are we going to generate? It's going to separate. So if it's going to separate, do we agree with the far left one?
No.
Okay. So then what about this one? Why?
Just it's not totally separated.
Okay, so this is partially soluble, or we could say it is a weak electrolyte. This term electrolyte, have you heard this before?
Yes.
Yeah.
What does it mean?
What you want in your water.
What plants need? That's what you have out of the drinking faucets. No. So electrolytes are things that if you put a wire, electrical current in one side, and you had a probe on the other, or a light bulb on the other, it would carry electrical current. And the reason is because it has ions dissolved in it. So a strong electrolyte describes something that dissolves fully. So then, both B is not a strong electrolyte, so we can get rid of that. What about the difference between C and D? How do we distinguish between those two?
The ratio.
What ratio, Carmen?
Ooh.
I'm just gonna say 2 and 2. I could be very wrong. Actually, that does not match the picture, so,
Can someone help out?
yeah, somebody.
New voice? Dustin?
I picked C because, ratio, but there's 2 potassiums per 1 sulfate.
So when this dissolves, we get K plus is one of our ions, and SO4 2 minus is the other. But that little subscript 2 tells us that we have to have 2 potassiums in order to make a neutral salt with 1 sulfate. So that means that we would have 1 2 minus with 2 pluses. If we look at the ratio in C, we see that C has the correct ratio, and that would be an appropriate diagram for K2SO4 being fully soluble, or a strong electrolyte. And most of our class ended up getting there. So I think this class needs to be like 30 minutes longer. How do y'all feel about that? Said no one in the history of the world. But hopefully you're finding it valuable that we spend time to work through the problems. Okay, so let's say that we have these 2 salts in solution. We have one container, the one on the left has potassium iodide. The one that's on the bottom has lead nitrate. We're going to combine these 2 solutions together. Before we do that, I want us to think about what are all of the ions that are going to be in solution together. So can I have someone shout those out? So we're going to have lead. What's the charge on that one? It's a transition metal, but we can see by the compound that it's in what the charge is. 2 plus. What else? We have nitrate. We have potassium. And we have iodide. All 4 of those ions are going to be fully dissolved, right? Like here they are separate, and we're going to throw them all together. So the question is, when all 4 of those ions are in there with water around them, when they bump into each other, are they going to say, screw you water, I'm going to go hang out with that other ion more than I like you? Or are they going to bounce off and keep staying with water?
They're not forget about the water.
So what if these 2 come back in contact with each other? Are they going to stay dissolved, or are they going to form a solid? They're going to stay dissolved. We know that because we can look at the trends on the solubility chart. What about the bottom 2? Those are also soluble. That's why they're separate over here. But the big question is, what happens when the diagonals, or the opposite pairings, come in contact with each other? Are any of those going to form a solid
Yes.
and fall out of solution?
Yes.
Which one? So if you don't have your solubility chart out, it might be worth looking at. And if we look at potassium nitrate, nitrate's always soluble, potassium's always soluble, so that kind of is a giveaway. So the real question is lead to iodide. What do you find when you look at that? It's going to form a solid. What's the formula? The I? So that's a salt that we're going to form. I'm trying to remember what questions I have set up here. So let's do that exact same process, but let's do that with silver nitrate and sodium chromate. And I haven't had you memorize chromate, so here's the formula for chromate. I want you to think about when those 2 solutions are combined. Let's actually go through a series of questions. First question is silver nitrate soluble? Click in your answer to that, please. And there's 3 ways you can answer this question. All right, we have a majority saying yes, it is soluble. How do we know? What are 3 ways?
Chart.
Chart. What else? Nitrates are always soluble. Third? I told you. It's aqueous silver nitrate. That means I'm telling you it's dissolved. So you didn't even look that up on your chart. Okay? So silver nitrate means that we have a clear solution. It has silver ions and it has nitrate ions. Do we need to do the same with sodium chromate? Aqueous sodium chromate? Okay, so you could look it up in your chart. It is soluble. I told you it's aqueous. Sodium is almost always soluble. Okay, 3 ways again. So that solution has 2 sodium ions for every 1 chromate. And the solution is clear, but it's yellow in tint because chromate is the yellow compound. So then when we add all of those together, what, if any, precipitates are formed with those 4 ions that we just discussed?
Are these the ones we discussed?
So let's do a couple more seconds, and I want to show something that's going to be very valuable for your homework this week. The good thing is we have your lab TA here, so if you end up showing up a couple minutes late to lab, he won't kill you. But I know that other people have lives, so I'm going to try not to be disrespectful. Okay, so what do we think? Are any of these going to form precipitates? We have 40 responses. Let's take a look at the responses. A lot of people are saying B. Why would we say B? Because we start with this, so we know those are soluble. Question is, if they cross, are they going to be soluble? We look at the chart, this one is insoluble. Other way to look at it too, sodium is almost always soluble, so we can kind of rule that one out no matter what it combines with. So here's the thing that happens when you add them together. You get this red precipitate that forms at the bottom. What I want us thinking about is how do we write this out in equation format? What you've probably been used to doing so far is what we call the molecular equation. That means, what did you start with? Right, our 2 aqueous solutions. And then you say, what did we end with? We know that this one is a solid because we looked it up in our solubility chart. And then this one, we say aqueous, but really that means that these 2 are still separate and floating around by themselves. So then what we do to be more specific and more chemical about this is we say, well, let's write out the total ionic equation. That means we're going to think anything that's an ion that's aqueous, we're going to write separate. So the next step is everything that's aqueous we write out as the individual ions. Right? We have 2 Ags, we have 2 NO3 minuses, so we write those separate. We have sodium and we have chromate, we write those separate. And on the right side, sodium and nitrate, we write those separate. The last thing, and this is what you're going to need to do for the homework, is you're going to need to say what stays the same on both sides. What spectates? What watches and doesn't participate in any chemistry? And we're going to call those spectator ions. So can anyone tell me what ions don't change from left to right as far as their state, their aqueous nature? Sodium and nitrate. So then the net ionic. This says what change actually happened. We take out the spectator ions and we rewrite the simplified equation. That's the net ionic equation. So these are the 3 steps that your homework is going to ask you to do. For a few of the questions in it is write the net ionic equation. And this is the process it wants you to go through. Notice you still have to balance it. You still have to determine if it's soluble or not. If everything had been soluble, then on this side, we would have said no reaction. But in this case, there was, so that would be inappropriate for this case. So that's where we're going to leave off the class today. I think you should be able to complete the homework with limiting reagents and ionic compounds. I will see you all tomorrow who wants to come, 10 to 12, e-task 125 for office hours. Saturday is still happening, yeah. Right? I'm not.
I'll let it be online.
I have that class.